All right, everybody, what we're going to look at today is describing a location in a distribution. Okay, that's the goal of the day, is to be able to describe where a location within a distribution. The first tool we're going to use is something called the percentile. Now, a percentile of a distribution is the value with p% of the observations less than it. So say, so we all took the PSATs and SATs, and some of you, like say I took it, and I was in the, I was in the 70th percentile. What does that mean? What does that mean to be in the 70th percentile? Well, what that means is that I did better. I did better than 70% of the people who took that test. So if you got in the 70th percentile in the SAT, if that's what your score said, that means you scored better than 70% of the people who took that test. Okay? Let's look at another. So we got Mr. Pryor's first test, and there's 25 students who took that test. Here's all of their scores right here. And you can see on this side of things, over here, there's a stem and leaf plot that shows this, kind of organizes the scores for us. So let's look at this problem right. Let's look at this right here. This Normand scores a 90, who earns a 92. Okay, right here. Norman earns a 72. Sorry. What's his percentile? Well, we can see that 72 is right over here, right? 72 is right there. And he scored more than, so he beat one person, okay? So we know that for Norman, that's going to be, that would be 1 out of 25 people. And that's going to end up being 0.04 if you do it on the calculator, or 4%. So Norman would be in the 4th percentile. That's what we would say. Norman would be in the 4th percentile. Katie, if we count that out, Katie, who scored a 93, way over here, she scored more than everybody. She's the top dog in this test. So what we're going to do with Katie is we're going to say, okay, so she's 24 people below her. There's 24 people who scored less than her. So she's going to be the 24 over 25. That's going to be, we do that on the calculator. That's going to be 0.96. Or in percentiles, it's going to be the 96th percentile, okay? So that's what we're doing. We're looking for how many people scored below that. So let's look at the two people who scored an 80. So we got a tie over here. We got a tie with the two 80s. But we know that 12 of the people, 12, if we count them, you can count all these scores right here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 people scored less than the two 80s, okay? So what that does is that puts them, that we take 12 divided by 25. That's going to be 0.48. So that puts them in the 48th percentile. Okay, so percentile is a measure of location because it tells us what percentage of people we did better than within the distribution. Okay, so if we're thinking of a number line, when you think of a number line, 90th, 195, 98th percentiles all the way to the right. First, second, third percentile, low numbers are all the way to the left. Okay, and then like numbers around the 50th percentile somewhere in the middle. Okay, so that gives us an idea of location. So we're going to relate that now to cumulative frequency graphs, okay? The idea of percentiles relates to this graph. Now, what we're going to do here is we're going to look at the inauguration age of presidents. That's when that's the age of the president when they get sworn into office in January. That's the inauguration. So, and we can see over here, we can look at this right over here that we have these ages right over here, and we have the frequency. So like between 40 and 44, there were only 2 presidents. 45 and 49, there were 7. 50, 54, there were 13, and so on and so on, okay? That's the amount of, this right here is the number of presidents that fell within that age gap, those age brackets. So let's kind of continue on. So that's the frequency. This table is going to do this right here. This over here, I'm going to use a different color. This right over here, on this side of things, that's what we were just looking at. That's that table. Now, this is relative frequency. So we know that at the time this data was taken, there were 44 presidents, okay? So relative frequency is we're taking that 2 and dividing it by 44. We're taking the 7 and dividing it by the total. And the 13, you can kind of see there, each of these frequency values is being divided by the total number of presidents that we had at this point when this data was taken. Okay? So we need to explain cumulative frequency over here. Now, where do these numbers come from? So you can see they all start in the same place of 2 presidents, but then it goes to 9. Well, that's because there was plus 7 presidents between there. So now we're adding up those presidents. So from 9, if we add the 13 presidents there, that's 22, plus the 12, plus the 7 here, plus the 3, that's how we get that cumulative frequency. We add the next group of presidents. Now, last but not least, we're going to talk about the cumulative relative frequency. So basically, we're just taking these cumulative frequencies and dividing them by the total. Okay, and you're gonna see that it's given in percents, and that's how we typically talk about things. Because our brains understand percents a lot better than decimals. So we're going to communicate these ideas within percentages. Now, the graph that you're going to see is this information plotted. This is what's called a cumulative frequency plot. Okay? This is called the cumulative frequency plot. I'm going to call it CFP. All right? Now, what we see here is that we can kind of see these dots kind of increase as we go along, right? So if we, this is what this tells us. This is each of those points as we move along the graph that we saw in that last table. Okay. Now, what's cool about these types of graphs is it tells us a lot of information because cumulative relative frequency is really similar, if not the same as percentile. So, if we wanted to say find the median, we would look for the 50th percentile right here. We would look for 50, and we would go to this point, and we could go down. So we could say, okay, which age is the median? Well, it's going to be 55, okay? 55 is going to be the median age, right? I'm going to write median here. So 55 is the median age. Now, say we wanted to find the quartiles, okay? Say we wanted to find the quartiles. Well, we could go to 75. We could go to 25 over here. And that's going to be approximate, boom. This is quartile 3, remember? That's 75%. The 70th, and that should be noted, the 75th percentile is quartile 3. 25, we'll just say it's approximately there, is here. Okay? And this is quartile 1. Now, you're going to see a question later that asks, hey, what's the IQR? What's the interquartile range? Well, we're going to take 60. So we know that quartile range is quartile 3 minus quartile 1. Okay? So in this case, we're going to take 60 and subtract 50. So our IQR is going to equal 10. Okay? Now, if someone were to say, President Obama was like 44 or 46, I don't know. He was in his 40s. Did that make him unusually young? Okay, did that make him unusually young? Well, let's say we have a president who's 45. Does that make him unusually young? Or let's say even 46. Okay, say we have a president who's like, or 48 years old. Let's say that. Well, 48 years old is only going to be about halfway there, so the 10th percentile. Okay, so 48 years old is only going to be that 10th percentile, which by definition, what we learned in the previous slides means that president, age 48, is only older than 10% of the rest of the presidents, which is not very much. So we could say within the scope of presidents, that president was unusually young at the age of inauguration, okay? Because he was only older than 10% of all presidents, okay? So that's how percentiles and cumulative frequency plots kind of blend together. And we can get a lot of information about location from a cumulative frequency plots. You saw that we got the median. You saw that we can easily get percentiles. You saw that we can identify certain ages to match those percentiles. And you saw that we were able to find the interquartile range. Those are some really key things that you can get from a cumulative frequency plot. Okay? Here, interpreting a cumulative frequency plot. And if you can read this statement on your own. I trust that you guys can read. But basically what it's saying is, as we look at this graph down here, we can see that down here where the slopes are really low, that means there's not a lot of presidents that are happening there. So if, like this section right here, this line is really flat. That means there's not a lot of presidents that are happening between the ages of 44 and 45. Okay, 45 and 50, we have more, but not a huge amount. Now, if you look at the slopes of these sections, these are getting steeper. This especially right here from 55 to 50, which steeper lines are going to show that more presidents. I believe that was a big 13 jump. That was the highest jump, if I remember my table correctly. That this shows that the most presidents that we see were ages 50 to 55. Okay, this line right here wasn't far away from that. And then we gradually peter off. You can see that we're gaining similar numbers of older presidents as we are younger presidents because the slopes of those lines are the same. So it's really important to look at the slope of a line when interpreting a cumulative frequency plot, or the slope of the segments, I should say, because it's broken up into pieces. It's broken up into each of these pieces, so you want to look at each of those pieces in the slope. And that's going to tell you a lot about what's happening kind of in the overall distribution of the ages of presidents. So focus on that slope. And what that's going to be able to, what that's going to help us with is it's going to be able to help us come up with the shape of the distribution when looking at a cumulative. Okay. And let's kind of continue on with this here. So if we were looking at this cumulative frequency plot and we wanted to sketch a histogram, what would that look like? Well, we know in a histogram, it's kind of that bar graph type thing, So I'm going to just quickly sketch one over here. Okay. Now, if I had a quick bar graph situation here, or a quick histogram, I would be able to see, I'm going to do this in green, this section right here, this section has a really low slope. So I know there's not a lot of numbers there. So it's going to be a really low bar. Now the next bar, I'll do in blue, is a little bit steeper than that, okay? It's a little bit steeper than that, but it's still pretty shallow. Now the next bar is going to be our steepest line, one of our steepest lines. Okay, so here we go. We'll make that really big. And our next bar after that is almost as steep, but not quite. Okay. Now our next two, I'll go back to green here. Our next two, you'll see that, we're slowly starting to peter off here. And then our last one is pretty low, okay? So right there, we're able to see, by looking at this cumulative frequency plot as a whole, by kind of using this pattern, we can see that, going by the slopes of these lines here, and they correlate to the histogram, we can figure out kind of the shape, because now that we see that histogram, it's easy to note that the shape of this is symmetric. Okay, this is going to be a roughly symmetric distribution. Okay. Now I'm going to do another example, a quick example over on the left side here. Say I have a cumulative frequency plot that looks like this. Okay, what is that going to be? There. Say I have a cumulative frequency plot that looks like that. Okay, that's the graph, that's the CFP. Well, what's the histogram going to look like? Well, I'll do the histogram in red here. Well, if you look at the beginning, I know that my slope is really flat. Okay, so I'm not getting much data, maybe a little bit more here and there. But then as I go more to the right, I'm getting bigger and bigger bars. Okay, so this is going to be skewed left. Okay, this is going to be skewed left. And that's kind of how we can correlate cumulative frequency plots to histograms, and how we can identify the shape just simply by looking at a cumulative frequency plot. As you get more practice with this, it gets a lot easier. Okay, so let's look at this example. I think we kind of went over some of it already, but let's kind of tie in some of our thoughts here. So, okay, this is the Barack Obama example. Barack Obama was the age 47, it says. Was that unusually young? So if we look down here, I'm gonna see if I can get a highlighter out. We look down here, we can see that Barack Obama was 47. I go up, and that is about the 11th percentile. Okay, that'll go over to the 11th percentile. Right here. Oh, I want to use a different color. The 11th percentile, which means Barack Obama was older than only 11% of the presidents we've had historically. So does that make him unusually young? Yeah. I mean, like, there's only a few other presidents, a very small handful, that he was actually older than, being the 11th percent, and being the 11th percentile. So that would be enough evidence to suggest that he's pretty young. Okay? So if we wanted to estimate and interpret the 65th percentile of the distribution, we can kind of see that over here. So we see that we get the 65 over there, and if you follow the lines, where does that bring us? Well, it brings us to 58. Okay, so the 60, what does that mean? How do we interpret that? That means a president That means a pres, age 58, is older than 65% of the other presidents. Okay? That's how we interpret that. Getting used to writing on this thing. So a president, age 58, is older than 65% of the other presidents. Okay, that's what it means when we're talking about interpreting using a cumulative frequency plot. That's what we're looking for. Okay. And remember, if you guys have any questions or whatnot, just shoot me an email, and I'll be happy. Well, if you're in my class, shoot me an email, and if you're just a person watching this video, drop a question in the comments, and when I see it, I'll answer it. My students, shoot me an email, and I'll be glad to help you if you have any questions about percentiles, cumulative frequency plots, or histograms, or anything really. So let's move. So this is check your understanding. I'm going to stop. I'm not going to stop, but I would suggest that you pause the video right now and check and try these problems out. In the next slide, I'm going to have the answers. Again, and if you're having a tough time getting the answers, again, reach out to me via email, and I'll be glad to answer any questions or Zoom meet with you, and we can figure out where the problems are. So take a quick pause right now, and when you come back, you'll see the answer slide. So here are the solutions. Here are the solutions. Not going to spend too much time on that. Not going to spend too much time on the solutions. Again, if you have any questions about why these are the solutions and you're struggling, please reach out. So z-scores. So last class, or in the kind of the previous lessons, we've talked about the standard deviation. Okay, so when we're looking at a distribution, especially a standard distribution, we're looking at the mean, and then we're looking at these standard deviations. So that's 1, -2, -1, -3 standard deviations, and this is the symbol I'm trying to draw, is that standard deviation symbol. I think I might have to draw it down here. That standard deviation symbol, and then we have 1, 2, 3 standard deviations on this side. Okay. Now, what a z-score is a standard deviation. It's just not 1, 2, or 3, which we typically look at. It's all the numbers. It could be any of these numbers, or it could be any number in between. So we're going to see the whole numbers and the decimals associated with the standard deviation, because not everything is going to be 1, 2, or 3 standard deviations away. It might be 1.5, 1.2, 1.8. Standard 2.11, -2.11. There's all sorts of decimal combinations that standard deviation could be. And what this is going to be called is a z-score. Now, a z-score is really easy to calculate because it's just this quick formula. So we're going to take the value in question that we have. We're going to subtract the mean and divide it by the standard deviation. And this process is called standardizing. So we're taking the data value and we're putting it through this process, and that's called standardizing, so that it fits within this standardized distribution that we have up here. Okay, so we're gonna, and the reason we do that is so that we can communicate better, because in a lot of cases we communicate with standardized standard deviations. And anytime we standardize something, that it makes it easier for us to communicate across all sorts of different platforms and through different sciences. So as a statistician, I know that the scientist I'm working with understands standard deviations. So I communicate it in standard deviations. It puts it within a unit we can all work with, okay, across all the fields. And again, we're going to use this formula in order to do that. So let's what that is. So back to Mr. Pryor's first test again. We are looking at these scores. So we're standardizing these scores. Okay. So if we look at this example, use green here. Katie scored a 93. Okay. So what we know about this test, okay, is that the mean score was an 80. That was the mean. In the standard deviation was 6.07, okay? So what we did in order to standardize it is we took 93, subtracted 80, divided by 6.07, and that gave us 2.14. Now, if we're interpreting that, you can read it right here. You can read it below. Is what that means is that Katie's result is 2.14 standard deviations above the mean. Now, if we look at Norman's score down below, Norman scored a 72. Now, 72 minus 80, that's going to be a negative number. It's going to be negative 8, and negative 8 divided by 6.07 is going to be 132. So we can now get to see what happens if we have a negative value right here at 132. And what does that mean? Well, that means Norman scored 1.32 standard deviations below the class mean of 80. Okay, and we'll talk about how we can evaluate that and create value for that next class. But we just need to know right now that Norman scored 1.32 less. And how do we know it's less? We know because that number is negative. How do we know that Katie did better than the mean? Her standard score was positive 2.14. It means she did better than the class average. Norman's negative standard deviation means he did worse than the class average. These are important facts kind of to know and interpret as we're going along in answering these things. Let's move. So using z-score comparisons, we're looking at this example. So we have Jenny from Mr. Pryor's class. So Jenny scored an 86 on her AP Stats exam and an 82 on the chemistry test. Mr. Goldstone told the class that the distribution of scores is fairly symmetric with a mean of 76 and a standard deviation of 4. And now what we're going to do is if we're looking at the problem here, we're looking at what we're being asked to do right here. We're saying on which test did Jenny perform better relative to the class? Justify your answer. So what we're going to do is we're going to determine her z-score for her chemistry class. So we can see that that work has been done for us here by subtracting the mean and dividing by the standard deviation. And Jenny has 1.5, so she did 1.5 standard deviations better than the mean. Now, if we calculate the statistics test, and I'll quickly do that out here, we would do 86 minus 80 divided by, I think it was like 6.07. So if we do that on the calculator, you're going to get 0.99. So she only did almost one standard deviation better than the mean. In both classes, she did better than the mean. Well, which class did she do better in? Well, if she's only worried about being compared to her peers, she did 1.5 standard deviations better than her class average in chemistry and only 0.99. So one could argue that she did better on her chemistry test, at least in relation to her peers. Okay? So that's how we can use z-scores as comparisons. We're going to use z-scores in a bunch of ways. It's really important that you learn how to calculate them and how to read them and how to understand them and what they mean. Because again, they tell us about the locations of specific data points within a distribution. And that can be powerful for comparisons, fact finding, and making and stating a claim, which is all things that we do. Okay? So again, here we are at another Check Your Understanding. Again, I'm going to ask you to pause the video. Do your best to go through this Check Your Understanding. In the next slide will be the answers, so we'll show you the slide. And again, if you have any questions or anything, reach out. Feel free to reach out to me via email, and we can Zoom and we can meet and we can talk about it. Okay? So, yep. Pause your video, and we'll see when you come back. Welcome back. Here's the solutions for that. And we can see these interpretations. It's really important that we write things when we're asked to interpret. We need to use the words, okay? We need to use words when we're asked to interpret, okay? You can see that we have the standard deviation down here at 2.35, and that was done with a little bit of algebra. Again, if you have any questions, feel free to reach out. I'd be happy to do any of these examples with you as you do your practice, or do any of your practice examples with you. Okay. So the last bit of things we're going to do is look at transforming data by adding or multiplying, dividing or subtracting. It's all kind of the same. It's all going to be the same stuff here. We're going to look at transforming data by adding, subtracting, multiplying, or dividing a constant. Okay, so what we're doing is we're looking at some data where students were asked to guess the width of their classroom to the nearest meter. There is the data, and there's a dot plot, and there is. And if we look down here, here's a summary. Here's a summary of. I'm gonna make it nice and full here. Here's a summary of that data, a numerical summary, which is some stuff that we should get used to. So it says at the top, let's do socks. So let's kind of have a starting point of where socks is for this. And so we're going to look at our shape. Well, our shape, if we kind of trace it here, that's skewed right. And I'm going to just do this real quick. I'm not going to use context here. I'm going to be a bad example. Outliers, well, we have some potential outliers out here. Let's look at the center. Well, the center, I'm going to use the mean, which is 6.02. So the mean is, my bad, is 16.02. And for spread, I'm going to use the standard deviation, which is 7.14. Okay. Now, what we're going to do is we're going to look at what happens when we transform this data by, again, adding, subtracting, multiplying, and dividing. So let's take what happens when we're adding or subtracting. They're kind of the same power. So when we're adding, we're going to add that constant number to the measures of center and location. So anything that is the center or a measure of location, so percentiles, quartiles, the median, we're going to add that number to it, okay? So say this class was guessing the width of their classroom. Well, say the teacher just like added a, he just said, well, what happens if we push the wall 10 feet wider? So we push that wall and it makes the room exactly 10 feet wider. What's that going to do to the distribution? Well, it's going to add 10 feet to the mean, median, quartiles, and percentiles. It's going to add 10 feet to those values. What it's not going to do is change the shape of the distribution or change the measure of spread. So we remember that that standard deviation was 7.06. I'm not going to add 10 to that. The standard deviation is still going to be 7.06. Okay? It doesn't change the shape or the spread. Example of this. So if we look up here, here's the original distribution. Now, what happened when we added, or was that the change? Let's see how accurate. By now, it's the peak. Actually, that's not the original. That's the new, because what they did was they subtracted 13 feet or 13 meters or units, whatever. They subtracted it, so you can see that it dropped, okay, by 13. And down in the numerical summaries, you can see it. So a couple things we want to notice. Notice that the shape between these two distributions is exactly the same. They're both still skewed to the right. We can see that the data is not any more or less spread out. And we can see that, however, if we look at the mean and the measures of, and the other measures of center and location, we can see that they've changed. So let's go down to this numerical summary. So the mean, this was our original, well, we can see that it got reduced by 13. However, our standard deviation right here did not change. Our standard deviation did not change. Now, if you look at other measures of location, like our median, you can see that went down by 13. Same with the quartiles around it, same with the minimum and the maximum. Another measure of spread here, I'll circle the interquartile range in blue, did not stay the same, did not change. The range did not change because those are measures of spread. So when we're adding or subtracting, it's not going to change the measure of spread or the shape, but it's going to change the center and the location. Okay? And again, the evidence in this example shows that and proves it. Okay? What happens when we multiply? Say we multiplied the room by a constant factor. We said, well, okay, picture this room being 25 times bigger. What's going to happen to it? Well, we're going to multiply the measure of center, location by that factor. Okay, so let's use 5 times. Say we're like, all right, I need you to imagine the room 5 times bigger. Or we're going to scale it down a third. So we're going to end up dividing by 3. What we're going to do is we're going to take all of those values, and divide by 3 or multiply by 5 or whatever operation we're doing, okay? Now, if we look at here, the big difference between adding and multiplying, and the same with subtracting and dividing, is we are going to change the measures of spread. Those are also going to get multiplied. The only thing that doesn't change is the shape of the distribution. That's going to stay the same. Okay? So the shape of the distribution is going to stay the same, where the measures of spread, IQR, standard deviation, those are all going to be change. So almost everything changes except for the shape when we multiply. Okay, that's a quick way of remembering it. Everything changes within the shape except for the shape when we multiply. So let's see this. Again, now you can kind of see it in our distributions. You can see the shape stays the same. You can see that the shape of this is the transformed graph right here because it's all super spread out. You can see that that is still skewed to the right, where our original is also skewed to the right. So the shape did not change. However, even in the dot plot, you can see how the data is more spread out. Okay, so that's where the spread is affected. Now you can see that the mean got affected by that multiplier, the standard deviation got affected by that multiplier, the minimum, the median, the quartiles, all of these values got affected by the multiplier because the only thing that does not change, I repeat myself, the only thing that does not change with that multiplication or division is the shape. Everything else, all of the other numbers in the number summary, except for like the sample size, right here, except for the sample size, will be multiplied or divided by that number. Any of the significant numbers will be multiplied or divided by that number. Okay? Let's move on. There's kind of some stuff that we're looking at. So let's look at this transformation. This is an example that a lot of people have a hard time with. So I wanted to look at that and do that with you. We have this Fahrenheit. And Celsius. We have this Fahrenheit to Celsius or Celsius to Fahrenheit calculation. So if we look at the problem down here, the first thing that if we kind of read everything, it says find the mean temperature in Fahrenheit. Does the thermostat setting seem accurate? Okay, so let's work on finding that. Now, so we know the mean temperature in Celsius is 8.43. Okay, now it's going to go through this transformation right here, where we multiply by 9/5 and add 32. So the thing that you need to ask yourself is, what type of value am I working with? Well, I'm working with the mean, which is a measure of center, and I know from our past talks that the center both gets added and multiplied. Okay, so what we're going to do, well, not actually in that order of operations, we're going to do multiply but then add. But both transformations happen to measures of center. We just went over the slide about that. So here's what we're going to do. We're going to multiply. So our mean is 8.43. So we're going to multiply that by the 9/5, because we'll do that transformation first. Using my calculator here. So that's going to equal 15.174. And then what we'll do to that is we're going to add the 32 to that. We'll add the 32 because it also gets that transformation. So that's going to be the new mean. The mean in Fahrenheit is going to be 47.17 degrees. Okay, that's how we would find that mean. All right. So now, if we look at the other part of the question that's important here, we'll look at, for the sake of time, I'm only going to look at this next one here. Calculate the standard deviation. Okay, so the standard deviation is a measure of spread. Well, we know that measures of spread only get multiplication. Addition doesn't affect them. Okay, so the measure of spread isn't affected by addition. So in this case, our standard deviation is 2.27. That's our standard deviation. And we're going to multiply that by the transformation that's taking place, 9/5. Again, we get that from the formula. So we take 9/5 times that by 2.27, and we're going to get the new standard deviation, 4.09, which is the standard deviation in Fahrenheit. Okay? Now, if we look at the last example, it says the percentile was 12 degrees. We're going to we would transform that. Since percentile is a measure of location, you're going to add and subtract it just like you did the mean. Okay? And that's how we're going to find the percentile one. I think that's going to be on my next slide for the solution. And bingo bango, just to highlight it so we don't see it, we're going to take that, so we don't miss it, we're going to take that 12 right here. We're going to take that 12, and you'll see that we multiply it by the 9/5 and add 32. And the new percentile is going to be 53.6. So, and you can read this solution later and give some of those interpreting words. Again, I don't want to make this too long by reading to you, but that's how we would do this. Okay, so that's how transformations work: addition and subtraction. Okay, when we're adding and subtracting that constant, we're only going to do that to the center. Okay, if we're multiplying, we're going to do that multiplication transformation to both center and spread locations. Okay, and I forgot to mention location. Adding and subtracting has the center and locations. Multiplying and dividing has the center, locations, and the spread. Okay, that's going to, all of those are going to be transformed. Okay, so moving on. Here's our last check for understanding. So you can click pause. You can click pause and do this over the transformations. Okay, when you come back, you'll see the solution. So pause real quick, and we'll see you in a quick minute. Welcome back. Welcome back. Here are the solutions to this. And this is going to wrap up the presentation. So I appreciate your watching. I appreciate your watching this video. Again, if you're in one of my classes, please feel free to reach out to me at any point in time. I'll be glad to answer any questions about the presentation or help you with any practice problems you'll be working on. And also, that being said, if you're not in one of my classes and you watch the video, I super appreciate it. And you can leave a question in the comments, and I'll see if I can help you out. So that's that. I hope you learned a lot, and we will see you when we see you.